Thank you. So I can't see the chat box.
Yeah.
So if anyone has a question, would you mind keeping track of those for me?
Yeah, I will.
And do you mind keeping your camera on so I can see you?
You want to see one face at
least one face, at least one familiar, friendly face. I hope you don't mind.
Yeah, that's fine.
Okay, great. So welcome every morning. Welcome everyone, and good morning is what I meant to say. I'm here to talk to you about my research interest and my love, which is geographic information systems. So first, let's look at this image. What do you see here? It looks a little bit messy, right? The world is complex. Half of it's illuminated, half of it's in the dark. We can see parts that are lit up. We see clouds. There's a lot of detail. There's a lot going on. And geographic information systems can help us parse out information and illuminate different features, different spatial patterns that might otherwise go unnoticed. Now, throughout this lecture, I'm going to teach you about how GIS works and the power of GIS. And I'm going to train your eye a little bit so that you can see nuances in maps that you might not otherwise notice. So for instance, I'm going to give you a little tip. So I used Microsoft PowerPoint to make this slide deck. And in Microsoft PowerPoint, you can pick stock art that they provide. So I searched maps, and this is one of the first ones that came up. And you might notice that Seattle is actually top center of this map. So that might tell you a little bit about who made the map. So Microsoft is based here just outside Seattle. It also illuminates the West Coast. So this already kind of shows you it's a North American centric view of the world. So the first part of this lecture, I'm going to give you examples of how you might use GIS in your own research. I'm going to also point out the ways in which you use GIS every single day. I'm going to talk to you a little bit about my research as it relates to GIS and specifically cartography. So cartography is the art and science of map making. So it's one part of GIS. And so in this picture, you can see someone holding a paper map. Most likely GIS was used to make that paper map. Then we're going to take a little break, and if you have any questions during that time period, that'll be great. And then the second lecture, I'm going to go into the process of GIS, some design and technical considerations associated with GIS, and some really key concepts. So first, for this course, we're all together going here. So can you help me with the pronunciation? The Utrecht Heuvel down in, how do you say it, Danielle?
Utrechtse Heuvelrug.
Heuvelrug. Heuvelrug.
Yeah. Heuvelrug, yeah.
And so that means like hillback? When I hear rug, I think of back.
Hill ridge. It means hill ridge.
Yeah. And so as soon as you look at the satellite image, you can really see this hill ridge. It really pops out. So this is where you will be going for your field research. Now, if we highlight this region, in your lab assignment, you're actually going to be working with this specific file, which is the outline of the park. This is a polygon feature. And with GIS, you can answer questions like, well, what type of soil might we find right here? And as a geographer, I know, and now you know, Tobler's first law of geography is everything is related to everything else, but near things are more related to distant things. So GIS can help you figure out what could be in a certain place, even if you don't know for sure. And we know that near things are more related than distant things. So let's go to the forest. And the first thing we want to do is we need to collect a set of sample points so that we can infer what type of soil might be in different parts of the park. So first we would go to the park itself. Then we would take a soil sample in different representative portions of the park. So here's an example of what a map might look like with different points where soil has been sampled, and then the types of soil in each part. Now, note these are random points. I didn't actually go and collect soil sample. I did look for soil sample data, but that took me down a wild goose chase. So this is just an example of what is possible with GIS, but this is not real data. So, okay, let's say we have now a set of soil points where we know what type of soil are in these points, but we want to know where that one red point was. So we could use a strategy called interpolation. So interpolation is kind of a fancy way of saying an informed guess. So it's an estimation of a surface value at an unsampled point based on what you already know about points around it. And there's many different ways to calculate or do these types of interpolation. And it's really important to think carefully about the real life phenomena before you pick a specific interpolation method, because every interpolation method isn't perfect for every sampling strategy. So that's just something to think about. Now I'm going to talk to you about one specific type of interpolation method called Voronoi polygons or Thesian polygons, depending on which software package you're using or which mathematician you choose to reify in the moment. So this type of interpolation, it's based on control points. So this is an animation. Now my sample points aren't moving, but this is to show you how the interpolation works. So polygons are drawn around each point, each known point, each control point. These are hypothetical points within a polygon, and it's called the area of influence. Now you notice that when the points shift, the polygon changes shape. And that's because the line is being drawn the halfway point between the two known points. And again, this is called a Voronoi tessellation. And so you're drawing a line equal distant between 2 points, generating a cell around each point. So this is what an output might look like. And so you can see clusters. The cells are smaller where the clusters are, and the cells are bigger when the points are more distributed. So it might look like something like this when we're done if we use the points from our case study. So what type of soil might we find here? Well, with this tessellation, we can then make an educated guess that, hey, right here, it's probably sand. It could be sand. And it was generated, again, using these known sample points. And this is what it might look like. And I love Voronoi polygons. I think they generate the most beautiful tessellations. And I've made them for my house because I think they look like really beautiful hipster art. But then you can also pick things that are meaningful to you to make them with. And I didn't make this up. And we see these tessellations in nature everywhere. So you see them in honeycombs and giraffes and coral. This one example in the top left is an example of cancer cells. So these sorts of tessellations occur everywhere. And I also want to bring up that this is a form of vector data. I'll talk more about that later. But soil sampling in the Netherlands is often done with raster data. So soil is a continuous phenomenon. It happens everywhere. And this country is so well mapped, and there's so much amazing data. The whole country has been actually covered and sampled using spectral sampling. So there's also raster data available. And if you want to look at this information more, this is an amazing web-based interactive map about soil in the Netherlands. And so this example is an example of geographic information systems. So GIS is all about taking different types of data, so abstracting reality, taking out the complexity and looking at one feature at a time, and then layering it on top of each other to find correlations, to use for decision making, to make interpretations of what's happening on land. So this is just kind of a classic illustration of different types of information that might go into a GIS. And this type of information is really relevant to government. Now, to get all of this information into a GIS, it takes a lot of work. And so first you have that messy real world. Then you have to decide what information to take and put into the database, that data entry process. Then you have to think about what type of analysis to do. So that would be like that, generating those Voronoi polygons. Then what type of visualization? So which types of colors, which visual variables do you want to use to then hopefully produce knowledge for that end user. Now you'll notice here that the arrow goes in both directions, because a lot of times the decision maker isn't making the map or doesn't have the technical knowledge to decide what should go into the GIS. So you might get to the decision maker and they might say, actually, this isn't what I needed. And then you have to go back and either reanalyze your data or collect new data. So this is really important to recognize each of the steps, because this is an expensive process, it's time consuming, and it really requires a lot of planning before you get too far down the line. So let's talk a little bit more about that data collection process, because really you are collecting spatial data every day. You're collecting it right now, knowingly or unknowingly. So traditionally, these GPS devices were only accessible to well-trained professionals who had a lot of money. But now we all carry them in our back pockets every day. So in a smartphone, you have an accelerometer, a gyroscope, you have cameras. These are all sensing devices. And then, of course, the GPS, the Wi-Fi, access to cellular network. And that's telling you where you are in the world, but it's also telling the apps that you use where you are in the world. And these are things we use every day. You can also use them to enter in data. So this is called volunteer geographic information. So VGI can either be active or ambiently data collection, and it's only as good as the sensor. So the sensor being you entering in that information, or as good as your sensor is in your pocket. So if you're in a city, sometimes your GPS doesn't work as well because the signal is bouncing off buildings, but that's why we then would go to, or your phone automatically then checks the Wi-Fi and some other sensors to make it more precise. But if you're outside if you're outside in a field, then your GPS is quite accurate. So you can contribute information, and then it's stored in the cloud, and then it's often served back to you through location-based services. So location-based services could be, an example could be like updated traffic conditions, and that is often calculated by who's on the road. So that's an example of a location-based service going back to you that's from volunteer geographic information. So like Google and some other apps are collecting information about where you are through VGI ambiently, and then serving it back to populations through location-based services. Another example of VGI could be like a restaurant review. So if you say, I really like this restaurant, it'll get higher ratings, and then people can read what your recommendation is, make a better menu decision perhaps. And so that's why this is a cyclical process. And then it's also used to populate web mapping services. So this is an example of one of the buildings that used to be a part of the downtown campus of UU. And look at this map that it's Google Maps. It looks like it's in 3D. There's so much data. Lots of buildings are labeled. It looks incredible. So Google, its data comes from a wide variety of different data sources. So some of it is your user content. Some of it is from governmental data that is openly available to all of us. Some of the data is manually entered by employees, and some is through automated processes. So Google Street View, they're collecting Street View information using these cars with 360 sensors on top. These cars are also taking LiDAR data, which is like information about the buildings around you. And they're also taking some environmental sensors like about air quality. So their aim is to have more data. The more data they have, the more users, the more advertisers, the more revenue. So it's a positive feedback for them. So that's some ways in which these web maps are being populated with data. And other examples are data are collected from other sources, such as your wearable Fitbits, your smart watches, drones. We can get a lot of aerial imagery from drones. There's action cameras, Internet of Things. So like if you have a thermostat, a digital thermostat at home, or I can't say her name too loudly, but Alexa, the Amazon and Google home devices. These are all collecting information all the time that's generating spatial data. And another example of some of these sensors that are presenting information in real time could be a weather map, traffic information, public transport. Data is everywhere. But something to think about is what gets counted counts. What gets counted becomes searchable. And that's really important to remember. So this is just an example of what an AI might look like when it's looking at that street view imagery. So Google this looks really scary, but really Google wants to take out cars and people when it's automating the street view level. But I like to use this GIF because it shows how images are being trained to identify objects. And then in the map above, you'll see what might be the output of some sort of automated classification process. So different buildings are labeled as apartment, church, garage, house, industrial. These different classifications then gets put on the map. And then you can make different analysis, assumptions, policy decisions based on what is in the resulting map. So let's go again back to that Google Street View. So this shows all the roads where Google Street View has driven. And if you think about those 360 images that they produce, they also use AI to then tag what it sees. So like those businesses, churches, whatever. So these are all the roads it's driven, and you think about these automated processes. Then you can think about the resulting map. So the map of that Academy Gebouw location, if you look on the left, this is the Google map. If you look in the middle, that's Microsoft. And if you look on the right, that's Mapbox. And Mapbox gets all of its data from OpenStreetMaps, which is all volunteer geographic information in their maps. So it shows, you can kind of see the priorities of each of these web mapping services just by opening them, just by looking at them. So you can see Google has lots and lots of businesses, Microsoft doesn't have much, and then OpenStreetMaps has more of what people find valuable in their neighborhood. So there's the academic building, there's some churches, there's a couple restaurants. So it really shows what's of value to those systems, something to think about. So data and maps are all made by people and machines. It's important to remember that people program machines, maps are made by machines, maps are made by people, so all of this is all intertwined. Another example is, this is output from drone imagery. So I'm really interested in how people can use drones for volunteer geographic information. Now, the benefit of using a drone is that you can enhance the temporal and spatial resolution of an area of interest. So yes, Google has amazing imagery, but you have no control over when that imagery is taken. So what if you want to show a phenomenon that changes over the course of a day, over the course of seasons? You don't have that control with the satellite imagery offered by any of these web mapping services. With a drone, you do. I showed examples of Utrecht, which has really high resolution imagery, but the whole world isn't equally, isn't equally captured. So this just shows, this was a 10-minute flight over my daughter's daycare center in Tacoma, Washington. And there's a lot you can tell by looking at this imagery. So you can tell that this is can you see my cursor? This is the daycare center right here. And we know from public health geography that the safest place for children to play are away from roads. So this is really safely nestled back in a community surrounded by trees, and luckily there's no thorough road. This is a one-way road you see here on the right. This is just one flight, and you can generate so much different usable raster imagery using drones. There's a lot of hope there. Drones are also really useful for disaster response, because oftentimes disasters are an acute event. So their before and after imagery can be really helpful in a disaster. And it's also important to think about different spatial information needs and different data requirements by different actors and different parts of a disaster. So there, some work I was doing in Tacoma, Washington, related to earthquake preparedness. And we were working with the fire department there because there's a lot people can do in their own homes to prepare for earthquake to make the firefighters' job easier after the occurrence. So we were identifying different places where people can communicate with disaster responders before a disaster hits, because during and after, it's too late. So I think this is really an important point. And also with my drone enthusiasm, I like to watch TED Talks, and there's this TED Talk by Robin Murphy, and she has been making these, she calls them disaster robots. She's been making them since like the 90s. And in her talk, she said, the challenge is not about the robots. It's about getting the right data to the right people. And that just really speaks to me, and it speaks to GIS, Geographic Information Systems, and Geographic Information Science. I just found that so motivating, because people get really excited about these toys, these gadgets, but the real challenge is getting the data to the right people. So I want to show you another example about this challenge of data. So I've shown a lot of examples from the global north. Let's move to the global south. So the Obama administration really pushed for this governmental open data movement. And actually, this also resulted from Google Maps and this shift to the read-write web. So when the internet first came out, when I was a teenager, when it became really accessible in people's homes, you could just download data, but you couldn't give data back. And then it started increasingly becoming possible to download data, but also upload data. And we saw this largely in social media. And then governments started to say, well, why can't we do this as well? Taxpayers are paying for this data to be collected. They should have access to it. And with public information, it was creating a lot of work for governments to go find the data and then give it to whoever asked for it. Why not just make it publicly available? So the Global North was doing this, had started to do this. And then Cape Town, South Africa was designated a World Design Capital in 2014. And as part of that mandate, they were encouraged to open their governmental data. So they were the first municipality on the continent of Africa to do this. So this is quite significant. And you may think, well, why does it matter? Well, okay, let's say you work in local government and you have to decide where to put a new library or a new school. And you're given this parcel data, like think about the cadastre. So these are property area. So if you're a city planner, where would you put the new school or library? Where would you invest in a new sewer line? Where would you put traffic lights? Well, I think we would put them in the northern part of this map, because that's where the people live, right? Well, let's add another layer of information. If you add the imagery, you start to see something else. There's like something going on south of those parcel lines. What's there? Well, actually, it's the townships. It's informal settlements. And these informal settlements don't have access to improved sanitation or toilets or running water. So this is what their sanitation looked like. And the government says, well, because we don't recognize those parcels, we don't have to give them resources. And so this is really problematic. Now, if we look at OpenStreetMaps, this is a screenshot from Carta, which gets its information from OpenStreetMaps, you can see that people have started to digitize those dwellings in OpenStreetMaps. And one of the parties responsible for doing this is an NGO called Violence Prevention Through Urban Upgrading. So VPUU is an organization that trains people who live in these communities to digitize their the roofs of the dwellings. So even though they might not own the land where they live, they do own the four walls and ceiling of the corrugated tin they've erected. So with this formalized digitization process, they're also given a deed to their house that they can use for a cell phone bill or whatever other bill. And if the person dies, they can pass it on to their children. So this is a really valuable document, and it's this process of GIS that really makes it valuable and official. And again, here's a screenshot of the same area in OpenStreetMap. So you can see people have entered in this data. So they filled in the blanks. So then if we look at this same area in Google Street View again, so again, these blue lines are where the Street View cameras have driven. You can see that they are not driving through these informal settlements, and they're not even going very detailed in some of these other communities like they are in downtown Utrecht. But if we do drop into one of these roads that have been driven, you can see what the informal settlements look like. And this is actually a storefront. This is what a storefront might look like in an informal settlement, but that store is not populated on Google Maps or any of these maps really. And that's because the AI hasn't been trained to recognize that as a storefront, or no one's entered that information who's visiting these places. So I've put a box around like the reference point so you can see where you are on each of these maps, but you can see in all three there are very few digitized places. And in fact, the Street View map is actually could be considered the most detailed compared to Google, which is interesting here. Then if we look at the globe in terms of where Google Street View has been collected, you can see it's very robust in North America and Europe, parts of Australia, and in South America. But it tells you really a picture about where Google sees value. So that was a picture of today. Now this map is really special to me. This is a historic map from the 1500s. Does anyone know, has anyone seen this map before or know why I'm particularly excited about this map?
I'm not sure, but maybe it's the first map where the map draw accounted for that we don't know everything about the world yet.
Yeah, that's very true of this map. Yeah, but it's so this map is really valuable to me because I am from the United States of America, and this is the first map that has used the term America to label North and South America. And what we know from this time period is that it was during the times of explorers, and the cartographer was Walden Z. Müller, and he made an atlas of the world. He was commissioned to make this atlas. So each of these panels is a page in a big atlas. And this atlas was recently found nestled in a castle in Germany. And then it was put on display at the Library of Congress, and my mom and I got to go see it. And the reason why this cartographer, Walden Z. Müller, named these continents America was for Amerigus Vespucci. Now, Amerigus Vespucci was not, historically, he's not known for being the first person to reach North America. But what he did was he wrote these little pamphlets and dispersed them to the public. So the public knew, oh, that's where Amerigus Vespucci was. And so that's how it got the name. So the cartographer named the continents of North and South America after Vespucci, who used social media of the time to talk about all of his adventures. So I just think that's really interesting. Another thing that strikes me about this map is at the time, the point was, hey, go to Africa. There are lots of riches there. We know a lot about the coastline. Look how awesome it is. Go there. So that's really front and center. Go to Africa and find riches. So there's a lot of different stories that are embedded in this map that can tell us a lot about history and the context of the time. Now, if you compare this map to this map, it's kind of telling the inverse story. Google is kind of saying, there's not much in Africa, don't bother. Whereas this map was saying, hey, there's a lot of money to be had there, go. And then if we compare it to this map, which is the Sustainable Development goal indicator 1.1.1, proportion of the population below the international poverty line, it's also showing that Africa now is, much of Africa is suffering from poverty. So I just think this is really an interesting connection that can be made by all of these different maps. And I really hope that I made it clear that with GIS, it's a very powerful tool, but we risk reproducing inequalities. So by teaching all of you how to use GIS, I'm really calling for an active engagement to combat inequalities through modern forms of map making. So even though it may seem tedious doing some of these lab assignments, and it might be boring, but these are really, really powerful tools we're teaching you. And very few people know how to do what you're learning to do. And very few people know what the social ramifications of these seemingly minute decision-making may lead to. So I hope that you enjoy doing all of this. So we kind of went through the data abstraction, what's happening in the real world, the data entry. Now I want to jump to the data visualization part. But first, are there any questions about what I've gone over so far?
No, not in the chat at least. Oh, there's a question from Cambo, I think.
Yes, hello. In fact, I got two questions because I got some background in land surveying, and I want to know what is the difference between, because you have introduced some polygon method in the first in your presentation. But for me, because of my background, I know that sometimes people would generate like using the triangulate method with the triangle. So what is the advantage of using the polygon method compared with the triangulate method?
Okay, so it just really depends on what you're looking for. So in land surveying, if you're talking about the triangulation method, you are talking about TINs, which are really common for generating elevation maps. And it really just, really TINs are also considered it's called Delaney method. So it's really just the inverse of a Voronoi. I guess with the Voronoi, it makes more sense for like soil samples because you can kind of guess that, like the whole point of the near things are more likely to be the same as far things. So if you're thinking about what's in between the two, the further away you get from the known point, the more likely it is to be that anchor point. But with elevation, it's always, it's always changing, well, depending on where you are. So TINs actually make more sense because you're connecting known points, and then you're kind of showing the relationship between two known points. So the method you pick depends on what you're trying to find, and it depends on what you're representing. So TINs make more sense for elevation because it's a continuous surface and you're connecting what's known between 2 points. But with soil samples, you kind of assume that a point is the same until it's not, like okay. You just have to think about the distribution of the phenomenon to know what the best interpolation method is. Okay,
thanks. And there's another question I want to know, because you said that you use drone for mapping some of the place, and I wonder if there's some like legal limitation of using drone here. Yeah, because I know that in some countries you need to be a licensed operator to use drone.
Yeah, so I actually haven't flown here, but it depends what you're flying for. So you can fly as a drone. Again, I'm not a legal scholar on drones in this country, but it's my understanding that you can fly legally as a drone enthusiast in designated areas under a certain height. And there is a map of the Netherlands to show exactly where you can fly when. And it shifts based on the military schedule, particularly in this region where you guys are working. But if you want to start selling mappable products from the drones that you're flying, then I think you do need a pilot's license. So it just depends on what you're doing it for and what you're doing with the products. And these laws are changing everywhere. They're different all over the world. It's really, really confusing. But the cool thing is they're becoming easier and easier to fly and easier to make maps with their products. So it's an exciting time, but also annoying.
Okay. Thank you.
Mm-hmm.
But Britta, of course, these laws aren't there for nothing, right? So
Yeah.
it's also about the protection of the privacy of the public, I would say.
Mm-hmm. Yeah. Because I mean, as much as I love drones, you know, when when there was the freezing weather and we were all peacefully ice skating, well, these drones were like flying over us and they're so loud. And to get pictures of people, they have to fly really low. And I was so annoyed. And I was like, oh. So no, and I mean, that's the other thing that is different. Like the legal thing is really interesting because, you know, my property line doesn't end at those where my deed says it does, but how high does it go? And that changes. There's different interpretations of that in different countries. So, yeah.
I also have one. Oh, sorry.
Yeah.
I have one more question, but maybe that gets covered later. I was wondering how to approach getting elevation data for the Heuvelrug. Like, do you know if there's a database for that?
Yeah, the Dutch have like so much data, and there's LiDAR data available for all of the Netherlands, and you'll learn about how to do that in the lab assignment. So I won't go over that in this lecture, but you will in the lab assignment. Or I'm calling it what do you call it? The tutorial assignment.
Okay, perfect. Thank you.
Yeah. Okay, so I'm just going to move on quickly and tell you a little bit about my recent book project, which is all about visualizing open data associated with the Sustainable Development Goals. And you may think, well, isn't there an online database for that? Well, this is what it looks like. So all the data are publicly available. Esri has donated, Esri's ArcGIS, it's a very expensive software platform, has donated a web-based software platform to make these data available, but it only gives you point data. So if you're looking at forest annual net change rate, can you tell me by looking at this which country has the largest annual net change rate? No, you can't. So then you have to make a series of decisions to then make a map to tell the reader what is the first, where is the most change occurring. And it takes a series of steps to do this. So I've written quite a few book chapters and a whole book about this that was recently published about how to take the specific SDG indicator data and make it into a map that's legible. And then I've also, parallel to that, a series of design questions to think about as you're making these analysis decisions and design output. So maps can really help to reveal complex structures that cause inequality by parsing out individual variables, illuminating patterns that might otherwise go unnoticed. So how do we take these just like flat files, these just files that have a country and a value, and then make this beautiful choropleth map? So first you have to, what's the nature of the data? Is it nominal? Is it ordinal? Is it ratio? Then you have to decide, do you want to make a map or a diagram? At what administrative level? So all the SDG indicator data are at country level. Then you have to think about what type of perceptual properties or what types of visual variables you want to use to illuminate whatever you're trying to illuminate. So if we think about this process, this is one of the centerfold maps that was generated for this book. So this is goal number 5 about the goal to achieve gender equality and empower all women and girls. This indicator is associated with target 5.5. So this really is showing women in parliament. So very quickly, you can see Rwanda actually has the most women in parliament, which may sound shocking, but it's actually the law. They have to have 50% or more women in parliament, and that's a result of their genocide. And other countries that have more than 50% are all highlighted here. We can see that the Netherlands is doing pretty well. Belgium is doing really well. So they have 20% or more, which is not equality, but yeah. So only 24% of parliamentary leaders are women in 2020. So this is all information you can very quickly see in this. This is called a choropleth map. So it's showing values with a gradiated color scheme, and it's at the enumeration unit of countries. Now, I was very specific with this map in terms of picking a color scheme. Now I'm going to look at the gender inequality index, and your choice of color really influences perception. So for the last map and this one, dark green indicates low gender inequality, which to me is saying, hey, that's good. But what if you changed the color scheme? Now the data are the same, the classification of data are the same, but suddenly the countries that seem to be doing well are dark red. You immediately kind of tense up and then think, oh, wait, they're doing bad. But wait, I thought they were doing good. So color choice, it's only one click of a button, but it can really influence what the reader sees on the map or how they interpret a map. So again, these are all 4 maps, same data, same classification, just different color scheme, and they each give you a very different worldview or interpretation or feeling. And so again, keeping on this emotional affect point, I had a master's student who was interested to see if, well, maps are supposed to deliver information quickly, and they're supposed to be easy to read, but do they actually have emotional affect? And so to measure that, she intentionally picked the most emotionally jarring indicator associated with the SDGs, which is female genital mutilation. Now, there's only data for this recorded in Africa. This is an illegal practice. So if you think about it, these numbers, how accurate could they be, because it's an illegal practice? And so then we did a usability study, and we measured feelings of before and after they viewed the map. And then we also did a couple of map-related tasks. So like, which country is suffering the most from this phenomenon? How many people are affected? And just a series of questions to see which map was easier or which map people liked more, and to measure emotional affect. So what we found, though, was really interesting that, so the map on the right is called a cartogram. So the shape and size of the country is distorted based on population. And then the map on the left is a choropleth map, just to show the rate of women who have undergone this, this horrific practice. And then so we actually found that people liked the choropleth map more because they're more familiar with it, but they spent more time looking at the cartogram and in really thinking about what they were looking at. And then what we found also that was kind of surprising was people said, it's just data. There was no emotional affect. So they weren't thinking about what they were actually looking at. They were just trying to quickly answer the questions, and they were interested why Africa looked so funny. So it was really interesting to read those findings. And there was a slight change in emotional affect, but not as significant as we would have expected. Especially considering that an estimated 200 million women and girls worldwide have undergone this horrific practice. So that was really interesting and something to think about. And if this is something that you're passionate about, you can actually add data to OpenStreetMaps about where women in this area can find resources to escape these practices. So if this is something that interests you, please check out these resources. So we went over a lot in this first lecture, and I'm right on time, 45 minutes. So we covered a lot about the power of GIS and cartography, but in the next lecture, I'll talk to you more about some details about how to do GIS. But first, let's take a quick break.
That's fine, Britt. I have one question.
Yeah.
Because there's a small discussion in the chat.
Oh yeah.
So you said something about a color palette map or a color plot map or a choropleth map or a choropleth map. So I was wondering, which one is it?
Choropleth map.
Okay.
So
Lawrence and Nora are correct. Yeah.
So a choropleth map, you pick a color palette.
Okay. Okay, let's take a 15 minutes break, I think, and then maybe we meet again at 10. Is that fine?
Sounds great.
Okay.
I'm here if anyone wants to has any questions or wants to chat during the break. Okay, so Lise, you asked about when you say voluntary geographic information, how exactly does it work, and what would you emphasize the voluntary in there? So this term emerged around the same time as the read write web term came up, and it came up before smartphones were really a thing. And so it really was talking about this active volunteering. So like actually adding data knowingly. But then with smartphones and app development, the first iPhone apps were collecting locational information and the user had no idea. So then people were voluntarily adding information, but they might not be doing so knowingly. So that term has shifted and evolved, but I'm using it here as this like umbrella term, like user generated content with geographic information involved. But if you accept the terms and conditions, you are volunteering that information. So it's debatable how you interpret that term and how legal lawyers interpret that term. But I think it was during my PhD, I think it was in 2013, I did a study where I actually wanted to study people's spatial cognition as a result from using location-based services, or like how did this new information in a place that they were receiving through LBS, how did that influence their experience in place? And so many people brought up this notion of privacy, and they knew that apps were taking their data, but the service they got in return was so valuable that they just didn't care. And that kept coming up again and again in my survey. Any other questions? Oh, and did that answer your question? Did that answer your question, Lise?
She said
Yeah.
that it sounds a little concerning for her, to be honest.
Yeah.
Rita,
Yes.
do you know which bird is in your gutter?
No. No. They're little and like very common looking. Okay, so it's 10 o'clock. Do you think I should just go ahead and get started? Okay, so yeah, let's go ahead and get started. Again, I can't see the chat box or any of you, so maybe shout if you want me to stop, or if you have a question. So again, in this part of the lecture, we're going to talk more about some technical considerations. So geographic information systems are the software used to aggregate data. It stores information about the world as collected in terms of different themes or layers, and they can be linked by geography. But this term GIS is quite an umbrella term, and it's not talking about one specific software or one specific database or one specific layer. It's the whole system. Now, geographic information science is the field of study used to improve some of these strategies, or like improving the interpolation method, or making adjustments to these GIS systems. So it's important to understand the distinction between GIS in terms of the software systems and the tools versus GIS science, which is the actual science of improving the tools within the system. And cartography falls within GIS. And this is just a graphic showing the expansion of cartographic research, analysis, and representation, and how the field has emerged. So cartography in the 1900s really just talked about thematic cartography. So those choropleth maps are an example of thematic cartography. That Walden-Müller map is also an example of thematic cartography. Then in World War I and World War II, we started having photogrammetry. So that's taking images from aerial vehicles, such as airplanes. So that started happening as a result of World War I and World War II, taking pictures of over enemy terrain to figure out where different militaries were gathering resources and working. Then in the 60s and 70s, remote sensing came about. So they started using satellites and satellite imagery to collect images of the Earth with multispectral imagery. And then, as I said, in the 90s and 2000s, then we started, really using this multimedia cartography, web cartography, more and more GIS. So these distributed servers, interactive visualizations. Then we had mashups, which is taking information from one source, so like Google Maps, and mashing it with information from, let's say, Marktplatz. And then you can see where people are selling their goods. So that's called a mashup, so putting two different types of spatial data together. And so we're in a really exciting time, I think, in this top right corner in terms of where we are with GIS and cartography. And then there's different user groups. So I've kind of given you this wide range of examples of GIS, but there's different types of users who are using GIS all the time. So the general public is using that Google Maps. So when I was showing you the example from Utrecht and businesses around you, that's the general public who are they're using maps on their mobile phones. They might be using tools like Microsoft Office or Excel, and they're using interactive slippy maps. So I'm pinching and zooming with the slippy maps. Then you have the traditional GIS analysts. So these are like government workers, scientists. So in this tutorial session, you are going to be using the tools of the traditional GIS scientists or the traditional GIS analysts. So you're going to be pointing to a web mapping service. You're going to be using what's called a desktop GIS. So it's going to be running from your desktop. And you may or may not use some basic programming. Then we have what's called cyber GIS or cyber GIS scientists, and they're using like big data, and they have to use parallel computing and advanced programming. And cyber GIS is always pushing the limits of what's computationally possible. So what's big data now might seem little in the future, and what was big data 15 years ago, it seems teeny tiny now. We can handle on our mobile phones now. So this cyber GIS scientist, the periphery is constantly shifting. So just to reiterate again, GIS combines information from several different sources. So if you think about a police station, they might want to know where all their police cars are or where ambulances are, and there might be sensors in the city to share other information. They might need weather information. So you can turn on and off layers to find new information, and then distribute it to other people on different desktops or mobile applications, and everything's being updated all the time. So GIS is really maps attached to databases. That's one way to think about it. So, but they're not just any database, it's a database with geometry. So that's what makes it a spatial database. And sometimes computer programmers think, well, it's just 2 more columns, 2 more rows, whatever. Like, no, it's actually more than that. Again, because of Tobler's law we learned, And also some other factors we'll talk about later in this, this lecture about what coordinate systems you use and which projections you use. So I saw someone put in the chat an example of what a difference a projection makes, but I'll get to that. So you have geometry and then the attributes. So the attributes are the non-spatial data. The attributes could be considered a flat file, or they might look like an Excel file. So it might have a numeric value. It might have a description of the features. So think about my soil sample example. In the attribute table, I had to add the type of soil that was there. So this is all information about what's being represented. And this is really where the value of GIS is. So you can come up with color codes or change the visual variable based on what's available in your attribute. You can't make a map without these very valuable attributes. So how can we use GIS? So again, it's a set of software for collection, storage, display, and analysis of spatial data from the real world. You can save data as a location. You can measure distances between 2 points. You can calculate elevation. You can calculate solar potential or soil erosion, model occurrences of plant species. Like the sky's the limit. Your imagination is the limit of what you can do with GIS. And again, I've already shown you some examples of what you can do with GIS. And what's really important to recognize is there's two different data types in GIS. So this vector data, which are points, lines, and polygons, or raster data, which is a continuous surface. So vector data, attribute data may be automatically associated with features that have unique identifiers, whereas raster data is a continuous grid where each cell will store a characteristic or value, and this value can be used to look up attribute data. So it might have like a land use classification, or it might have a digital number, a DN number, that has a value associated with it. So that's something to think about it. Different data formats are like, if you can, without even opening the data, just by looking at the file format, you can quickly recognize if it's raster or data. So GIF, PNG, JPEG, GeoTIFF, these are all raster data formats. Where vector data, it could be a PDF or GeoPDF, SVG, JSON, GeoJSON, KML, which is keyhole markup language. And this is what Google Earth uses, and it's a very common file format. And also shape files. So we will be using KML and shape files in our tutorial assignment. So a little bit more about vector data. They're points with an X and Y coordinate. The lines consist of 2 points, with multiple nodes or endpoints, and then connecting the dot between these dots. And then polygons consist of nodes to make a closed shape. To demarcate an area. And these vector models are useful for storing data that has discrete boundaries, like countries, and each entity has its own set of values. So vector models are useful for storing data such as country borders, land parcels, streets, capitals, but it's important to make sure that the features are positioned accurately, that the shape of features are represented correctly, and they're not good for representing spatially continuous phenomenon like elevation or temperature because they're not accurate enough. And they can become potentially complex, especially for polygons that lead to long processing time or analytic operations. They could basically freeze your computer if they're too detailed, if there's too many nodes in that polygon to make it look too perfect. And so for this reason, there are generalization tasks to kind of reduce the polygon, to make it smaller. If you don't need that detail, this is an example of different common generalization tasks. And this is from the SDG book that I co-authored. And there are different techniques to do this generalization depending on the type of feature. So it's really common to smooth a coastline to reduce complexity if you don't need too much detail. And the level of detail required, again, depends on the project you're working on. If you are just using your map for navigation to get from point A to point B, you might not need the same level of detail as if you're deciding to build a house, or find a sewer line you need to dig up to find a leak. That would require much more detail and precision. So these are things to think about as you're picking if you need to generalize something or not. What is the end map going to be used for? And other considerations associated with visual variables. This is just kind of a diagram to show, if you're showing a point or a linear area, how size can show magnitude or height, or the orientation can communicate something different. So these are all examples of visual variables that can be used for your end cartographic product. Some common tasks in GIS: you might just need to zoom to a layer, or identify a feature, or view an attribute table, or you might need to do some pretty complex topological operations. So find a point that's nearest to this point, or find a point along this line, or what area is in this area or intersects, or these are all very common and easy to do typological relationships with GIS. You can also run advanced spatial statistics using GIS. This is a really common function in GIS for science and environmental science in particular. Again, this is from my SDG book. Something to really be aware of, though, is the modifiable aerial unit problem. Again, this is a concept that other information scientists that haven't been trained in geography might not be aware of. And this is what I mean by it's more than just a added X and Y column. No, we need to think about the way in which we decide to aggregate our data will influence the spatial phenomenon at hand. So in this example, we have the exact same set of random points generated, but if you choose to count how many are within each grid, or if you change the form or the style of the grid, then it looks like the spatial phenomenon changes. So, and this is known as the modifiable area unit problem. So this is really tricky. Now, if we look at this at the SCG data, for example, so here we have forest area as a proportion of total land area per country in the year 2000. If you look at the map on the left, this is the value for each country. And if you look at the map on the right, the data have been aggregated by what the UN calls M49 regions. So then North America is put together, then regions of Africa are amalgamated. And so then again, based on the modifiable area unit problem, the phenomenon looks much different. Now, you might not be too worried about it because it looks like, the Netherlands on the map on the left looks quite similar to the map on the right. But what about Chad? If you look at Chad on this map, the proportion of land area is about 3, the 0 to 3 classification. But then on this map, Chad, all of a sudden the forested area as a proportion of total is 50%, 57%. And the UN is using these maps to allocate resources, to allocate funding. So to certain countries, if their numbers shift, that could mean a lot to them. So this is an example of how the modifiable aerial unit problem can be translated in real life. Something else to think about in GIS are projections and coordinate systems. Now, the world is round, as we know, and so every projection, you're compromising something. It's inaccurate. And so when you're picking a projection, it's important to think about how the Earth is being distorted. So this is an example of Web Mercator, this final one. And Web Mercator is used for web maps. The Mercator projection was developed for navigation back in Walton Z. Mueller time. so to travel the oceans. But it distorts, it's an equal angle projection, but it's not an equal area projection. So the area gets very distorted by the poles. So somebody took a screenshot and showed how the area of Greenland looks way bigger in the Mercuric-Cator projection versus this interrupted Holstein projection that we see here. So that's something to think about when you're picking a projection at the global scale versus the scale of the Netherlands or whatever feature you're trying to highlight. So again, let's look at SDG indicator 1.1.1. I showed you this one already. If you want to play, like I'm going to show you a series of screenshots from this website. So if you want to play with it yourself, I really encourage you to. It's a really fun tool. So if we look at this map, it's centered on Africa, where the most poverty occurs. But if you change the central meridian, so this is also called the Molly-wide projection, and this projection trades accuracy of angles and shape for accuracy of proportions in area. So this is an equal area projection. And as such, it is used where the property is needed, such as maps depicting global distributions. And then here's another projection. Again, it's equal area. And this time I shifted the central meridian to where I was born in the United States. And that shifts, again, what we notice about the map. So what we very quickly see is, wait a second, Canada and the US don't have any data. That's strange, but that says something. And then if we shift again, this is an interrupted Holocene map, and it's focused on the Pacific Islands. So small island states are the first to feel the effects of climate change, yet they contribute the least emissions. And because they're so small, we often don't see them on these global maps. So we were interested in figuring out ways to illuminate them and then also illuminate how they're missing so much data. So here's an example of a map like that. We did a usability study with this map, and people were able to do the map related tasks, but they hated it because it split the land masses where the majority of us live. So again, this is from the SDG book showing how the central meridian really shifts the view of the phenomenon of the map reader and what we think about it. Oh, okay. Then something else to consider, especially for our lab, are coordinate systems. Coordinate systems are so important for accuracy. So when we're working on the local scale, we really need to work with whatever the localized coordinate system is. And it's important that all of your data layers are using the same coordinate system, or else they won't match up. And then there's a lot of opportunity for incorrect map making. These coordinate systems are also important because the gravitational pull for the Earth is different, and the Earth is bulbous. It's not a perfect sphere. So these projections that I'm showing at the global scale are assuming that gravity is equally distributed and that the Earth is a perfect sphere, but it's actually a spheroid. It's bulbous and it bulges in South America. So these local datums are so important for accuracy. Also, like Google Maps is not perfectly accurate. Their borders are not accurate. And there have been some horrific examples of some developing countries using Google Maps, using Web-Mercator projection for governmental projects and construction projects, and then digging and starting to build in the wrong place. There was a terrible example of this on the Costa Rica and Panama border a couple years ago. And then I think about it here all the time in terms of infrastructure, subsurficial infrastructure. If you're not working with the right datum, then you don't know where to dig or where to build. So this is so important, and it's important for our lab because the lab assignment won't work if you're not using the Amersfoort datum. And the cool thing about the Amersfoort datum is there's actually a national monument at the 00 center of the Netherlands in Amersfoort. I don't know if it's open right now, but it's a really, really cool place to visit, and they have a really amazing museum there. And I don't know of any other place that has something like that. And in the United States, it's so big, each state has its own coordinate system, and some states are so big, they have multiple coordinate systems. So it's something to think about. And the different kinds of coordinates are used to position objects in a 2D or 3D space. Spatial coordinates are also known as global coordinates, are used to locate objects either on the Earth's surface in a 3D space or the Earth's reference surface, so an ellipsoid or a sphere, in the 2D space. So specific examples are the geographic coordinates in a 2D or 3D space and the geocentric coordinates, also known as the 3D Cartesian coordinates. So planar coordinates, on the other hand, are used to locate objects on flat surface of the map in a 2D space. So examples are the 2D Cartesian coordinates and the 2D polar coordinates. Sometimes conversions are required to match coordinate systems. Thank God GIS does this for you, but it will often alert you that these changes are being made. So it's just important to recognize when this is happening and if you're saving them or not, or if they're just being reprojected for the project to overlay properly. So these are really important for data overlays, accuracy, borders, where to build, etc. Any questions so far?
No.
What do we see on the map that is a bit distorted? Like, yeah, they are on the right side. What is this showing?
Okay, so this is an example of how the Earth is bulbous, and this is actually showing the gravitational field. So this is actually a more accurate representation of what the world actually looks like. We always see this perfect sphere, but in real life, it's bulbous. So that's why these datums and coordinate systems are so important, because it's really the localized accuracy of your region based on the gravitational pull and so the Netherlands is the center of the Netherlands is Amersfoort, which is why our local datum is called the Amersfoort datum. And then the whole country is perfectly mapped in relation to that 0 point in Amersfoort. And so it's perfect for the Netherlands. And different parts of the world have these localized datums, because if you look at the world, it isn't perfectly sphere. So we can't assume that the spatial coordinates are going to be perfect in the Horn of Africa, because look at how the gravitational pull is different and all these other variables. So then you have to have ground control points and a localized datum for that region as well.
Britta, I also have a question.
Yeah.
So every country sometimes use their own like local coordinate system.
Exactly, yeah.
But sometimes I can imagine that you from another country want to access the coordinate system, but use somehow a global coordinate system in general. And then you probably have some transformations or something, right?
Yeah.
But how does that exactly work?
Yeah, so in your lab, this is so funny. So I've been working in GIS for like 20 years, and I always learn new things. So in QGIS, well, all the GIS systems have an inventory of all the localized datums and the global coordinate systems. So the global and local coordinate systems. And you know who made this inventory? Do you know? The European Gas Association or something. And I talk about it, if you watch those little videos that I made, I talk about it very briefly. So because the gas industry is working all over the world and they have to be so precise, they went ahead and made their own repository of these coordinate systems, made it open source. So that's what QGIS is using. That's what ArcGIS is using. That's what all these web map services are using. And then, so what I was saying too is that what in good practice, you will reproject all of your data into the coordinate system for the local area in which you're working. But the joy of GIS is that you just click 2 buttons and do it. Or if you forget to do it, you'll get an alert and it'll say, hey, do you want to reproject? And then it'll tell you how it's happening. And it's calling this open source inventory of all the different coordinate systems to do those conversions. It's incredible. I hope that answered the question.
There is one question from Cambo.
Yes. Hello. I want to ask one question because although yes, we know that the control point is in Amersfoort, but the Earth is constantly changing as well, and sometimes probably we need to update the geodetic. We need to use geodetic survey to update the data, and I would like to know that, for example, in Netherlands or in EU, like how often would this data be updated? Like,
Ooh, that's a good question. And I started reading about that while I was preparing this lecture because that soil map, that web soil map I was showing you, so it linked to this whole article about how the NAP system in the Netherlands isn't sufficient for the soil subsidence issue affecting the Netherlands. So the coordinate system, I can't speak for the Netherlands. I can't, this is not my area of expertise at all, so I can't speak for anywhere really. But I don't think they're updated. I mean, I have no idea how often they're updated. And it should be made publicly available in metadata. So metadata is data about data. And it sounds really not fun, but it's so important, and you can learn so much by going through it, and it's really important to keep it updated in your own data. So I was once at a conference though where, like, you know, I'm making these location-based services, I'm making pretty maps, but I don't really care about the gravitational pull of the globe. I don't work at that level. But there are a lot of Earth scientists who do, geomorphologists, these sediment scientists. And so their biggest complaint of these desktop GIS is that they don't account for the gravitational pull or how the Earth's surface is shifting, exactly what you're talking about. So a lot of that, these scientists have to update themselves or whatever the accuracy of your specific domain requires. But in terms of who updates it and how often, I don't know. And I think it depends on your domain.
okay, thank you.
Okay, so I'm going to move on a little bit. Another example of something you can answer with a GIS is routing. So like if I am in Utrecht and I say, hey, where's the closest poke restaurant? Is it going to give me the Cartesian distance? So that would be that blue line, the direct, oh, it's only, you know, a kilometer away. Or is it going to give me the Manhattan distance, which makes more sense because that's the route I'm going to walk, and that distance more accurately represents my distance. So when you're working with GIS, it is important to recognize the difference. How are you measuring space? How are people actually traversing space, etc. So that these are different things we need to think about. So I've been generally talking about vector data. But what about continuous phenomenon? So elevation values. So this is an example of the Netherlands. So this is where I'm standing right now. I am right here on the edge of town. And this is the Linge River. And you can use this LiDAR. So LiDAR data are really precise elevation data. And it's really, really expensive because you collect it with a low-flying airplane that's sending laser pulses, and then the pulses are being bounced back, and it's centimeter resolution. So this file is like 2 or 3 gigs. It's huge, and there's a lot you can do with it. You can tell a story about a landscape. So I was really inspired by this National Geographic article, and this geographer for the state of Washington, his name's Daniel Coe. He had been working with LiDAR data to measure changes in fluvial geomorphology. And if you look at a picture, I should have put a picture of the Mississippi River here too, because there's just one channel. And then this is a historic map that someone made, like best guess of the geomorphology of the area. And then Daniel Coe used his technique of LiDAR to prove that this scientist was right. And it's just incredible how accurate this map on the left is compared to the map on the right. And LiDAR data is often used recently in archaeology, because also the benefit is you have the first return of the light, which is usually the surface, and then the second return, which in densely forested area would be the trees. So you can turn off the second return and have a bare earth elevation model versus forest canopy. So there's a lot of great implications for forestry industry, but also for archaeology, because in these densely forested areas in Mexico, they're learning a lot about Mayan ruins that we once never knew because it was under the forest canopy. So I think we're at the tip of the iceberg about what we can do with this LiDAR data. But I'm just so excited because it's not widely available, but it is in the Netherlands. The whole country is available for the Netherlands. And so you can run a lot of statistical analysis about the surface. So if I were to just take a normal elevation map or just look out my window, it's flat. It is so flat here. But then if you start playing with the visualization and start playing with the statistics in the software, different patterns start to emerge and are illuminated. And so you can see here on the right, I'm playing with the different standard deviations, and then you can start to see changes in the landscape. And this is really beneficial for continuous phenomenon. But something that we often do, which is dangerous, is so this point data is not continuous. And here so this is we're going back to that soil sample data set that I showed at the beginning. And I made that Voronoi polygons. Here I tried to make a heat map, or it's in GIS we call it a kernel density map. And it's not appropriate here because it's showing density of where I took the most points, but it's not really showing what type of soil is where. And these kernel density maps are really dangerous because they're often used for point data, but it's giving this false impression that a phenomenon is continuous. So an example could be like crime data. So if you're putting all these points of crime and then making this density, it looks like the crime happens everywhere, but crime is temporal, and just because it happened at one spot doesn't mean it happens over this continuous surface. So just because you can do a certain interpolation method or a certain visualization technique doesn't mean you should. And I think I already shared this slide, so I'm going to skip over it.
Britta, can I ask you a question?
Yes.
So this LiDAR data, is that available to everyone, or?
Yep, it is. Yeah.
And where do we get it?
So I think you get it in the lab assignment. Remember when you when the one part where you're downloading those tiles, one of the outputs that you can choose from is the LiDAR data. And then the TIFF that you're going to download in this assignment is a processed image from LiDAR data.
Okay, so the students can download it when they're also in a tutorial.
Yes, yeah.
Cool.
But the elevation model that they're using it's derived from LiDAR data. And I mean, I wouldn't recommend downloading LiDAR data unless you have a very specific reason to, because it will crash your computer. Like, these files are huge. But if you want to play with it, I mean, definitely you can download it, and there's tons of tutorials available if it is something that interests you. So the most common GIS software to do a lot of these functions that we've talked about so far are ArcGIS and QGIS. So ArcGIS is run by a company called Esri. Esri was started by Jack Dangerman in the 80s, I think. He dropped out of Harvard in the 70s. He was a landscape architect, and he started this product. And he's been really revolutionary because he's made it free to universities and educational institutions, but then it's also government, it's basically government standard, but then he profits by selling it to government. So you learn it in university and then you go into business and work government and then you're like, hey, we have to use this project. And so right now you do have a free license to ArcGIS because you are a university student. So I would recommend checking it out if you're interested. But for this lab, we're going to be using QGIS, and we're using QGIS because it's free. And so after you leave the university, you can still use it. It runs on Mac or PC. ArcGIS only works on PCs. And QGIS has so many accessible tools. There's so many plugins, and you're going to learn how to use them. And it's a fantastic resource that you can use the rest of your career, and it's constantly being updated. And yeah, are there any questions about the two main desktop GIS softwares yet? I really use both. They both have strengths and weaknesses, and if you can use one, you can really use the other. And there's a lot of tutorials available for free online to use both. So because you're learning QGIS, you will have no problem using ArcGIS and vice versa. So don't worry too much about that. And when we talk about GIS software, we generally talk about this desktop GIS. So that's the QGIS or the ArcGIS or ArcGIS Pro. And when I'm talking about desktop GIS, I'm talking about the processes and the software and the data all live on your localized machine, on your computer. So traditionally, you needed to have a pretty powerful computer to run GIS. Now for this lab, all the data are small enough, and QGIS is, we're not going to install every single plugin, so you'll be fine. But if you think about a government, or if you start using that ArcGIS Pro or the Esri products that the university are offering, increasingly GIS is moving away from the desktop and more on distributed GIS servers. Now, the names of these softwares that are being run on the servers change all the time. So don't get stuck on the names, but this infrastructure, this stack relatively stays the same. So the spatial database that are often running in the background, PostgreSQL it's a database specifically for spatial data. It's an open source database specifically for open data. And that's really, really powerful and good to know. And then there's also tons of different software libraries and extensions that are running in the background as well. So what makes desktop different from web? Well, it's these cloud distributed data centers. So the data are no longer stored on your localized machine, they're stored on these services. And increasingly, you can access and run those processes on these servers from your desktop web browser, not even, or through the, you interface with these web browsers through your desktop GIS. So increasingly, there's this shift from working on your desktop to working on the web. And I'm seeing like huge shifts like in the past year. So it's something to be aware of, especially in this lab. This lab assignment will be pointing to some web mapping services, and that indicates, okay, that imagery, that data, that's not living on your machine. It's pointing to these servers. But then when you download the shape files or you download all the data you need from Blackboard, then you unzip the data. Let me repeat this many times. You download a zipped compressed folder, and then you need to extract all the individual files to your local machine. So it's important to conceptualize where is your data when, and because you're essentially like, when you're working in QGIS, you're pointing to different data. So it's important to know where that data is. And if your machine crashes, sometimes it's good to know, why did it crash? Is it because I'm working with too much data? It's just important to be aware of. And so these machines are incredible. So I actually got to visit the United States National Supercomputer. And I don't know if we can play this or not, but it's incredible. It's so loud. Okay, I don't know. I don't think it's going to play, but these supercomputer, like it's loud and it's really, I have a hard time thinking about, okay, you know, I'm just pointing to another data set. Oh, I'm loading a satellite image, but these images are somewhere. And when you're asking a computer to do something, like these server farms are lighting up and we're like being cooled down and it's requiring resources. So it's just something to think about. So WebGIS is a model for enabling convenient on-demand network access to shared pool of configurable computing resources that can be rapidly provisioned. And when we think about web maps, it's important to understand how a website works. So HTTP actually stands for Hypertext Transfer Protocol. And the URL stands for Uniform Resource Locator. So where is that? When you say send me the URL, you're asking for that path, that address. And so you can have a URL for a local document on your own machine, or you can have a URL with an HTTP, meaning it's being pointed to a publicly facing cloud. It's the internet. So the first part of the URL identifies the actual computer where it's situated, and the second part is the location of the file on that actual computer. So it's listing the directory and the subdirectory. And if you want to learn more about the autonomy of web maps, this is a great, really quick and beautiful slideshow about it. But if we think about web map, like what I'm just describing, so here HTTP is saying, okay, this is on the internet. Map time is the domain name, but it's also pointing, the domain is attached to a certain server, so that computer. And then the subdirectory is the anatomy of a web map. And then this is the slide number. So this is the location of the file. And so it's calling that specific first slide. So it's something to think about. And then some examples of some cloud computing that's accessible to you is this are openly available from Google Earth Engine, and Google Earth Outreach is working with Google Earth Engine. So Google has actually made an inventory of all the satellite imagery ever collected from Landsat all the way back from the 70s to the more recent and better Sentinel European satellites. And you can access all of them through Google Earth Engine for free. And all the processing is happening and all the data storage is happening on Google servers. So, you know, this supercomputing for GI science may sound really abstract, but you can do it yourself for free at home using Google Earth Engine. And here's just a screenshot of a map one of my GSS students made just last year. So I know most of you are first-year students, but in your third year, you have to do a thesis project. And if this is something that interests you, please keep me in mind and contact me in 2 years when you're taking that course. So some examples are you can make animated maps of deforestation over time. So this is again calling the satellite imagery from the Amazon, and you can see this like fishbone deforestation happening over time, which is just heartbreaking. And you can specify how the pixels are colored and what to illuminate. Some other publicly available data sets through Google. This is an example of, I think, temperature, or no, it's a climate model, also available on Google Earth Engine. So focusing more on what you'll learn in this tutorial, you're going to learn to calculate distance between different points. You're going to learn how to answer spatial queries like how many people live further than 250 kilometers from this point of interest. You're going to be able to digitize your own data and make your own map. And to do all of this, first you need to download the data from Blackboard and get started. Also, before the tutorial, please install QGIS because it takes longer than you think. You have to also install Python and some other libraries. So please do this before the tutorial because you don't want to spend the whole tutorial just installing QGIS. So please do that on your own. And then let's say you love doing all of this and you want to do more. Here are some examples of open data available in the Netherlands. This is just a screenshot, and this is an active link to open data for Utrecht. And if you really love it too, there's this initiative called Humanitarian OpenStreetMap, Missing Maps and Youth Mappers, and it's organizing projects to help communities experiencing disaster. Where do they need data right now? And it's something you can do from home. And it's just organized efforts to update maps for those in need. So you guys all have the skills to do this. So I encourage you to do it if you have some free time. So that's all I had prepared for you. If this intrigues you and you want to read more about my work, here's a link to my my website. I also have some interactive maps you can play with there. And I'm open to any questions.
Thank you, Britta. Because we're already quite over time, I think there's still left for a few questions, but those who want to already install the software, go ahead. So are there any questions? I think it was really clear, Britta.
Okay, great. Sorry for going over time.
No, it's okay.
And everyone's still here. I'm impressed. A lot of people stayed for the whole thing.
Yeah. So then if I can take the floor for just a few seconds for those who are still here. First of all, the groups for the GIS tutorial you can find on Blackboard. Also check out your group number because your group number needs to be answered in the survey, and for which you're gonna send in your answers. And also read the guideline, because you don't just, I don't know, bluntly call the student assistants within your Teams group. So first ask these questions in the chat, and then we can help you out afterwards. Also in the guideline and in the manual, it's stated what you need to download and where. And we are working with QGIS, as Britta told you, so you can download it. I had already an email that some students had some problems with opening the software. For especially on Mac. So for those on Mac, I think it has to do with your Mac software. It can state that that they think it's very old, outdated data of old, outdated software, and it's malicious or something. So for the Mac users, you can go to the system preference and then go to privacy and security. And if you look all down below, it says something about grant access to execute the software. So that's just for the Mac users who run into problems. Furthermore, for all of you, we would like you to save the answers, written answers, already in a Word file, and the screenshots, save them in a separate folder. That is because the survey which you have to send in your answers, you cannot save it as a draft. So you need to fill in all the answers and then send it to us. Furthermore, if something goes wrong, especially with the survey, we don't know yet, then you can rearrange the hand-in for you, that you can still send in your answers. Then there is one thing more I would like to tell you, is that this survey is made by Survey 123, and Survey 123 is a very good accessible app for you also to use. You can make your own surveys, and so this is just a survey where you can fill in the answers, but you can also imagine that you can use the survey to ask questions to participants, but also to fill in your soil data, for example. And it also has the possibility to track your location. And this can save you a lot of time. And by bringing your phone into the field, you can fill in the data, and it sends immediately to the cloud where you can download it afterwards on your own computer. And I think that was it. There's one more thing I would like to ask you guys, is that I have only one participant for the course feedback group, and I would like to have at least 2 or 3. And some of you already emailed me that they were quite disappointed, for example, with the topic allocation. And these are exactly stuff that we need some input from you guys. So how can we rearrange this for next year that you are more satisfied with the topics, you are more interested about the course? So please, hopefully 2, 3 people can send me an email. It won't be long. It's only maybe 50 minutes, 30 minutes. We can also talk about other stuff, maybe your career, for example. But please send me an email so I can have some input about that. I think that's it. So we created these, on Teams, we created these channels. Please go there. All of your different groups have allocated a TA. I once again want to thank Britta. So please give her an applause, because it was a really good lecture. I really liked it. And yeah, maybe some of the students will see you again in the future with some courses. I think environmental impact assessment. And also the thesis is a course which they can contact you. And yeah, thank you very much, Britta. And we see each other at the tutorial for some of you.
Great, thanks. Bye, guys.
Bye, guys.